In the previous lecture, we did an overview of the quantum Hall effect. In this lecture, we will look into the mechanism of quantization of electron orbitals in K space, Landau levels, and the electron orbitals in the real space, their quantization, and flux quantization. Okay, so let us start with a picture of free electrons in a solid, and you have the states in the K space for free electron, which forms a Fermi sphere, which we discuss in detail in one of the previous modules. And two dimension, this is kind of the illustration where you have K states which are separated by 2 pi by L, where L is a dimension. Okay, and we calculate the Fermi energy, density of states, and all these details using this picture. Okay, and the energy, total energy, which is the energy in all the three directions, sum of the energies in all the three directions, that's h bar square by 2m, kx square plus ky square kz square, and you know this is kx square plus ky square plus kz square is the k square, which is the radius for that, for radius which defines the electron with a specific energy. Okay, E. So it's equation for basically a sphere. Okay, now in two dimension it will be circle. Okay, now what we are interested is what happens to these states, or to put it correctly, what happens to the distribution of these states, which are now evenly distributed in kind of a square lattice in this case, okay, or a rectangular lattice depending upon the dimensions of the material. Now you have a magnetic field. Say that field is in the Z direction. So you have a magnetic field, B field, which is in the Z direction. Okay, that is the picture. That is the situation. Now when you have magnetic field, and you also assume that the electron can undergo cyclotron motion without undergoing any collisions. That means the material is clean with enough mean free path. There are not any scattering events when it undergoes the cyclotron motion. Okay. Now, the moment you apply magnetic field, parallel to the direction of the field, nothing happens, because the magnetic field cannot affect anything in that direction. But in the plane where the electron motion is perpendicular to the field direction, it will undergo a cyclotron motion. Okay, that means we have a system which undergoes a cyclotron motion, but it is quantum mechanical. Okay, that is a simple harmonic motion, right? The moment you have simple harmonic motion in the plane, that means the x and y, kx and ky are no more independent, because you have, they are connected by the radius of that circle, which defines the cyclotron motion, right? Now, from simple quantum mechanics, basic quantum mechanics, we know that the energy corresponding to that motion is given by n plus 1 by 2 h bar omega, where E perpendicular defines the energy which correspond to the motion perpendicular to the field. Okay, and omega c that is cyclotron frequency is given by EB by M, where E is electronic charge, M is the mass, and B is the field. Okay. So now the total energy you can write as E kx, ky, kz, where the kx and ky thing, this thing, you can together you have to write as n plus 1 by 2 h bar omega. And kz, the z direction, the motion is not affected. The dynamics is not affected. There you can write k h bar square, kz square by 2m. That term is separate. So now, if you look at what has happened to these states in the case space, is you have a uniformly distributed periodic state in the case space. Okay. Now, this kx and ky are no more good representation. Instead, what you have is n plus 1 by 2, that is some radius for the cyclotron motion, which is given by kx square plus ky square. That's the equation for a circle. So the condition is kx square plus ky square should be a constant, that is given by n plus 1 by 2 h bar omega c. So E perpendicular, this is nothing but, originally it was h bar square by 2m into kx square plus ky square. That was this term originally, right? Now those kx and ky are no more now good representation. What you have is, you have states which satisfy the equation kx square plus ky square is a constant. That is nothing but circles. So all those states which are now which were distributed evenly has condensed onto circles. Okay, because all these k states need to be in one of the circles defined by this radius. That's a radius square. Okay, so all the k states now have condensed onto these circles. These circles are called Landau levels, and this quantization condition is called Landau quantization condition. Landau quantization condition, and these levels are called Landau levels. This is the case for when you have a two-dimensional system. Now in the three-dimensional system, you have also kz squared, that is along this vertical direction or along the direction of the applied field. But again, the same condensation applies for the motion in the plane, which is perpendicular to the field direction. There, what you have is, you have, instead of this circle, you have tubes with radius. These radius for these tubes are actually, these radius for these tubes, okay, are quantized by this condition again. Okay, so these are called Landau tubes. Okay, these are Landau tubes, and these are Landau levels. Okay, that is what we have for a three-dimensional case and two-dimensional case in the presence of a magnetic field, and we call this a quantizing magnetic field because these fields should be comparatively larger than that is used for a normal classical Hall effect, because the condition here is the cyclotron motion, that radius should be, or that circumference should be, or that time scale for completing that complete circle should be shorter than the mean free path or the scattering time. Otherwise, it will undergo scattering and you will not get a chance to complete its circle, and the whole motion will not be simple harmonic and you will not have any quantization. Okay, so the condition here is, you have far less number of scattering events and electrons will get ample time to complete or undergo the cyclotron motion. That is the condition. Okay, and this happens at somewhat higher field. Again, what field you will observe this phenomena depend upon the purity and cleanliness of the material, and how many scattering centers are there, what is the scattering time, and these are all eventually related to mobility. So you actually need materials with really high mobility. Okay. So now this is the picture, and remains that we are going to start discussing the quantization of the orbitals. Now you know that these states are actually lying on certain levels or tubes which are quantized. Okay. Now let us look into what happens to these electron orbitals, okay, in the K space. So first we will go with the K space, then we will consider what happens in the real space. Let's consider the three-dimensional case first. It's very easy to come back to two-dimension because we just need to drop that Z component, which is just a addition to the whole thing, which doesn't have any B field dependence. So we can easily drop that term later, okay? Or you add that term later. It doesn't matter whether you consider or not consider. It matters only when you consider the quantum Hall effect eventually, okay? Now, let's consider now only the XY plane, okay? From the plane which is perpendicular. Now you have the energy now quantized as given by this term here, n plus 1 by 2 h bar omega c. That is the harmonic oscillator energy level. Okay, where omega c is the cyclotron, frequency. And this is h bar square k. I have now added a subscript n to represent that. That is the nth level. That is the k state for that k state represents the nth level, where n is this quantum number. Okay. This energy h bar square kn square by 2m is given by the energy of the harmonic oscillator for the specific level. Okay. Now, where kn is the radius, kn is nothing but knx plus kny, because nx and ny, because now nx and x and y are not really well defined states. Okay, the moment you apply a field, but they got mixed now. Okay, so the radius of the electron orbital in the K space is given by this kn square, which is, you can invert this relation here and you will get 2m omega c divided by h bar, this relation. And the area in the K space is pi kn square, this of the form pi r square. That is, I am represented by skn. K represents subscript k says that is K space. N says it is n state. That is given by this term here. Okay. Now what you are seeing here is the area for any given B field cannot take any arbitrary value. It's always 2 pi e by h bar n plus 1 by 2. Okay, n is 1, 2, 3 like that. Okay, for any given B field. And the area difference between two Landau levels, okay, that area difference in the K space is difference between successive Landau levels. Okay, that is 2 pi e b by h bar. What that says is this cannot take any arbitrary value. This is 2 pi for any given field. That is 2 pi e b by h bar. That is a constant. So if you take any successive area difference between any successive Landau levels, that area difference is always same. What I am trying to say is, for example, I am taking these two Landau levels. Area difference, this area is same as the area difference between these two Landau levels. They are all same. Okay, that's what I am trying to say. Now, until this point, we have considered only the energetics in the plane. But this motion in the kx and k in the xy plane, that is perpendicular field, is given by n plus 1 by 2 h bar omega. This is a harmonic oscillator potential, or it's a parabolic potential with successive n goes from 0 through, higher values. Okay. Now you can also consider that there is a motion this direction. Okay, then this term also will come in picture. So for a three-dimensional system, we need to consider the z direction also. In that case, these energies are represented by these parabola, which are shifted by n is 0 or 1. But now you will see a crucial point here, which is very much applicable when you discuss the quantum Hall effect. That is, if I have an electron which is sitting on this n is equal to 1, okay, this is given by n is equal to 1 is basically, that is a Landau level. Okay, n is equal to 0, n is equal to 1, 2, these are the Landau levels. Each of these represent different Landau levels, right? Different orbitals. Now the same electron, this axis is energy axis. The vertical axis here is the energy axis, okay? It's energy axis. Now for the same energy, either that can sit in this corresponding orbital here, or it actually can sit in this orbital here. The only difference between these two is how much energy is being partitioned between the plane and the z direction, because the total energy is same. If I have a total energy which is given a constant, how much of that energy is partitioned for the xy plane motion versus how much is that partition for the motion in the z direction. What I'm trying to say is, if you have a particle with a constant energy, that could be lying in n is equal to 1 or n is equal to 0 Landau level. But the transition from n is equal to 1 and n is equal to 0 is possible if there is a motion or there is a scattering allowed in the z direction. Then that actually can scatter from the n is equal to 1 state to n is equal to 0 state. That is possible. Okay. So what that means is inter-Landau level scattering or the condensation in the transport that you will not see if you have an inter-Landau level scattering, that you will see when you discuss the actual quantum Hall effect in next lecture, that you will not see that if you have a third dimension. The third dimension will make the Landau level mix and you will not see a quantization effect in the transport. Anyway. Now, but the message now we have is the orbitals in the K space are quantized by this relation. Orbital area is quantized and the area difference between successive orbital is same for a given big field. Okay. Now let us try to look into what happens when you consider the real space orbitals. Okay. So again, this is a free electron picture. Okay. So I mean, of course, that is very much applicable because the two-dimensional electron gas is actually a free electron gas, which obeys the Fermi statistics, Fermi-Dirac statistics. Okay. So the energy again is given by half mv square, where v is the corresponding perpendicular motion, which is v is equal to omega into r, and that is again given by this quantization, a quantized energy n plus 1 by 2 h bar omega c, where omega c is the cyclotron frequency. From that we can extract what is the radius square in the real space, okay, and the area of the orbital in the real space. Rn represents the radius correspond to the nth level, okay, or nth orbital in the real space, okay? It should be real space. The real space. So the area is given by pi Rn square, okay, and that is this term here, where SR represents the R space and N represents nth orbital. And here also what you are seeing is this area is quantized, but the B dependence is actually now inversed, okay. In the previous case, you have B in the numerator, and here you have B in the denominator. Now you can look at what is the flux enclosed by the orbital, okay. If I take this B and multiply that by the area, that is B dot S or S dot B, that is the total magnetic flux enclosed by that orbital, and what you are seeing is that is actually quantized. It's kind of really surprising, because just by simple treatment, what you are seeing now is the flux enclosed by any orbital is actually quantized h by E, where h by is the flux quantum, okay, quantized flux, magnetic flux is n by n plus 1 by 2 h bar, n plus 1 by 2 h by E. So now the area difference between successive orbitals, consecutive orbitals, delta SR, is also quantized. It's constant for 2 pi h bar by EB for any B field. Okay. So this is the delta S for the n for delta S for two successive orbitals, difference, area difference, and we have the same delta S in the K space here, okay. Now the product of this area difference, the K space and real space, is 4 pi, it's a constant, and it should be a constant because these two are actually inverse in dimension, and you should get a quantity which is unitless, okay, is basically 4 pi. And from this relation, you can take the B and multiply by this area. So delta S into B, that is h by B. That is the flux enclosed between two successive lambda levels is always h by E. That is, it doesn't matter what field it is given, okay, because it's always h by E, it is independent of the field, okay. The flux enclosed between two successive lambda levels. The flux enclosed by any lambda level is quantized. Any orbital, real space, okay, not lambda levels. Any real space orbital is quantized. The flux enclosed between two successive orbitals is h by E. This is a real space, okay. Now we have flux quantization here, okay. This is flux quantization. Okay. So, but this flux quantization, which actually says if you have a cyclic path, then the flux of cyclic path for the electron, the flux enclosed within that loop is actually proportional to the quantum level n, and it is quantized in n. Okay. The same flux quantization, you can get it from a completely different picture. Okay, that is by using Bose-Sommerfeld quantization condition. This flux quantization we will encounter in various discussions during the course of this lecture, this set of lectures. when we discuss Arno-Bohm effect, when we discuss weak localization, when we discuss superconducting, interference devices. Okay, in various contexts, you will basically come across this flux quantization. Okay, so what we just saw is a flux quantization which is being revealed without considering anything. Okay, anything involved in intricate. Now let's look into the flux quantization which is used by Bohr to explain the atomic structure or shell structure of the atoms, orbitals, the stationary states for electrons in an atom. So the Bohr-Sommerfeld quantization condition, what it says is the integral of the generalized momentum taken over a closed orbital is quantized this way. Okay. But in our specific case, what we need to consider is we have your momentum h bar k, which also has a contribution from the vector potential E into A. Okay. So the h bar k is E into R cross B. This you can get from the force is dk by dt into V cross B. So when you integrate it, you will get R cross B. Okay. H bar k E into R cross B. Now you have this term here and you also have this term. Okay. When you substitute these two, this and this for P in your Bohr-Sommerfeld quantization condition, you will get this equation. Okay. Okay. Now this R cross B dot dr, you can interchange cross and dot, and you can get R cross dr term, B dot R cross dr term, and this A dot dr is the line integral over the vector potential on the entire path. Okay, that you can replace in the area integral. That will be the flux enclosed, and this term here is nothing but the twice the area of the orbital. R cross dr is 2 into S. That's a simple mathematics which calculates the area of the orbital. Okay. So when you substitute all these, what you are going to get is you have to minus E into phi. That's P dot dr, that is minus E into phi, but that is given by this quantization condition. So from this, what you can write is the flux enclosed, the phi, is actually quantized in h by E. Okay. So this quantization of the magnetic flux, which is enclosed by a closed orbit, you can prove that, you can arrive that from the very basic Bohr-Sommerfeld quantization condition. But the same condition is what you are also getting by a simple calculation of the area in the real space, then multiplying area of the orbit in the real space under the action of a field and multiplying that by the field. You are getting the same condition. All right. So now what we have seen in this lecture is the formation of Landau levels under the action of a magnetic field and also Landau tubes in 3 dimensions. Then the quantization of the electron orbitals in K space and real space, and the flux quantization in a closed orbital in real space. Okay. So in this premise, what we will go over in the next lecture is the Landau levels, the density of states in the Landau level, and the dependence of this Landau level or the radius of the Landau level on the B field, and how that is going to affect various transport and electrical and electronic properties of the solid. All right.